Today we are going to be talking about graphs. Okay, a graph consists of a set of vertices and a set of edges connecting various pairs of vertices. So vertices and edges. The edges may be straight, curved, or and should either connect one vertex to another or a vertex to itself. So, got this graph here for an example. You got V1, V2, V3, and V4. All right. E1's there. E2, E3, and E4, and E5. Okay. V5, V6, E7. Okay. So some terminology. The E's are edges. They connect the various vertices. A edge connects two vertices, like in the case of E1 connects V1 to V4. Two edges that connect the same two vertices are said to be parallel. That's one on. I can't spell. All right, parallel. A edge that connects a vertex to itself is called a loop. And a vertex that is not connected to another by an edge is said to be isolated. So this one is over here is isolated. So some definitions here. I'm going to read the formal definitions. A graph G consists of two finite sets, a non-empty set V of G of vertices, and a set E of G of edges, where each edge is associated with a set consisting of either one or two vertices called endpoints. The correspondence from edges to endpoints is called the edge-endpoint function. An edge with just one endpoint is called a loop. Two or more distinct edges with the same set of endpoints are said to be parallel. An edge is said to connect its endpoints. Two vertices that are connected by an edge are called adjacent. And a vertex that is an endpoint of a loop is said to be adjacent to itself. An edge is said to be incident on each of its endpoints. Two edges incident on the same endpoint are called adjacent. A vertex on which no edges are incident is called isolated. So let's the edge endpoint function. You have, this is E6 over here. So E1 is V1, V4. The E2 is V2, V3. And V2, E3 is V2, V3 again. E4 is V3, V4. And E5 is V4, V4. And E6 is V6, V7. I was getting ahead of my notes here. Oh, okay, yeah, it's actually, little goof here. These are sets, not ordered pairs. So and that's E1, E2, E3, E4, E5, and E6. So that is the edge endpoint function, where the domain is the edge and the codomain is the pair, the set of vertices that are connected by the edge. Just as a to visually represent some of the terminology in the definition, V2 is adjacent to V3 because an edge connects the two. Okay? E4 is adjacent to E1 and E5 and E3 and E2, but E4 is incident on V4, which is also has the edges E1 and E5. So E4 is adjacent to these edges. Now, there is also what's called a directed graph, which consists of a non-empty set of vertices and a set of directed edges, directed, which has an arrow on it, where each is associated with an ordered pair of vertices, not a set. If edge E is associated with a pair VW of vertices, then E is said to be directed from directed edge from V to W. So that's so it would be E1, comma V1, V2, and that is an ordered pair, indicating the origin of the directed edge and the destination of the directed edge. And E2 likewise would be E2, V3. The uses of graphs include things like the power grid, transportation, organizations, how they're organized, and different groups are related, indicated by an edge, like groups that would work together would be connected by an edge. Now, the degree of a vertex is the number of edges that are incident on V for a vertex V. Loops are counted twice. So if we go back to this graph, the degree of V2 would be 2 because there's 2 edges incident on the vertex. Oops. V4 would have a degree of 4 because loops are counted twice and then 2 more edges are incident on it. Let's see here. So example here. Just as example of how you would have like a transportation network represented by a graph, where the directed graphs, the directed lines would indicate connections by airplane. So you could easily see by the degree of each node or vertex on the graph, Denver and New York are the busiest airports because they have the highest degree of edges on them. So they would be the busier airports. And whatever else that implies. Obviously the air traffic network in the United States is much more complicated than this, but it's used for routing and resource allocation, that sort of thing. There's another use of network graphs, creation of knowledge bases. It's too complicated for me to put up on the board, but it is on one of the slides in section 1.4 of the slides on Canvas. It has a knowledge base indicating, what periodicals are, how periodicals are structured, and you can represent knowledge in the form of a graph and infer new information based on how the connections are made and that sort of thing. But I invite you to look at the slides on the periodicals knowledge base slide in the slides on Canvas. Graphs are a surprisingly short section in this group, so we are going to go on to, and that will wrap up chapter 1. We're going to go ahead and start chapter 2, which is the logic of compound statements. So I'll go ahead and clear that up. Okay. The logic of compound statements. Logical form and logical equivalence. That's not right. It's equivalence. All right. An argument is a sequence of statements aimed at demonstrating the truth of an assertion. So the logical form is a sequence of statements I can't write today. Sequence of statements demonstrates the truth. All right. An assertion at the end of the argument is called the conclusion, preceded by various premises. Followed by premises followed by a conclusion. In logic, the form is distinguished from its content. So the form, we use variables, manipulate the variables in these arguments, and demonstrate the truth of the assertion without regards to the actual content or the value of those variables. Let's see here. Analysis will not help you determine the intrinsic merit of an argument's content. It will help you analyze the form to determine whether the truth of a conclusion follows necessarily from the truth of the premises. So, you can analyze the structure of the argument and see if it is a valid form of argument and determine later on the content, you plug in the content into the variables that you use. But logic is the science of necessary inference or a science of reasoning. It is the science of reasoning. So, let the variables represent components of an argument. Let's see here. If the bell rings or the flag drops, then the race is over. So, if the bell rings or the flag drops, then the race is over. How would you, what variables would you use to represent this? Let's say P, bell rings. Q, flag drops. R, race is over. So you can manipulate P, Q, and R in multiple different ways. And you could say from the by manipulating the variables around and reconstructing it to say if the race is not over, then the bell hasn't rung and the flag hasn't dropped. Now, have you? How many of you have taken digital logic before? Okay, good chunk of you. You recognize the logic operators in these statements? Three basic logic operators? And what's the third one? No. Not. The inverter. So if the race is not over, then the bell has not rung and the flag has not dropped. Or back over here, you have or. Yeah. So there's parallels here to digital logic. We'll get more on that in later sessions. But now in this structure here, you can substitute some different things. Let's say if x equals 2 or x equals minus 2, then x squared equals 4. I effectively changed the variables, changed the content of the variables. We'll get into the symbology of this in a little bit, but the argument has the same form. You see that? I just changed the value of P, Q, and R to be x equals 2, x equals minus 2, and x squared equals 4. So if you can then, because this is a valid argument here, a valid inference from the previous statement, if x squared is not 4, then then x is not equal to 2, and x is not equal to -2. It's the same argument structure, the same logical form, just different values for the variables. And that's what this section is going to discuss in a little bit more detail. Let's see here. So to put it in more simplistic terms, if P or Q, then R. Therefore, we get a little bit of symbols here, get a little symbology here. If not R, then not P and not Q. You can take this concept and use it in other statements, like if Jane is a math major or Jane is a computer science major, then Jane will take Math 150. Jane is a computer science major, therefore Jane will take Math 150. If Jane is a math major and Q is Jane is a computer science major, R is Jane will take Math 150, then it becomes if P or Q, then R. Q, therefore R. A lot more abbreviated. Some definitions, some more definitions. A statement or proposition is a sentence that is either true or false, but not both. So, statement is either true or false. Not both. Compound statements. You can use these symbols to represent different operations. I mentioned a few minutes ago the not operation. The and operation, which is like an upside down V, and or. Easiest way to remember this is the symbol for and looks like an A without a crossbar, and the symbol for for or is the other one. So just remember which one is the and The or is the other one. Order of operations. Parentheses first, like in math, like in most math classes. Then nots. Then and. Typically it's then and. Oh, and or. Left to right. Parentheses are used to clarify the order of operations. Let's see here. A little example. It is not. Use H for it's hot and S for it's sunny. So H equals it's hot. S it's sunny. So represent that symbolically. It is not hot, but it is sunny. How would that be? That would be not H and S, like today. It is not hot and it is sunny. It is neither hot nor sunny. That's going to be this weekend. Not hot and not sunny. Or you could put it anybody recognize that's taken digital logic recognize what I did with that one? What is it? Yeah, I know, but from digital logic, what rule allows you to go from this to this? What law? De Morgan's law. And got to remember that. It's going to come up on later on in this chapter. So truth values. Definition. If P is a statement variable, then the negation of P is not P. It has the opposite truth value from P. So I've had this discussion with other students in other classes, but these are truth tables. Digital logic, you deal with state tables. Slight difference. So not P. You have P, 1, 0, not 1 and 0. I'm stuck in digital logic. True, false, not P, false, true. That is a truth table, indicating that if P is true, not P is false. If P is false, not P is true. Okay? P and Q. Let's do P and Q. Now, to write a truth table, for those of you who have not had digital logic, you write all the possible combinations of your input variables. For one input variable, there's only two possible combinations, or two possible values, true or false. Because as stated earlier, a statement can either be true or false, but not both. Likewise, with two variables, you have four possible combinations. True, 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 false, false, true, false, false. That's all the possible combinations. In fact, for n variables, there are 2 to the n combinations. So let's get back to P and Q. P and Q. Well, P and Q is only true if both P and Q are true. So it's true here, false everywhere else. This is also called the conjunction of P and Q. Okay? Then there's P or Q. Anybody guess what the value for P or Q would be? The values would be? Yep, all be true except for the last one. Because if either one or the other is true, then the disjunction of P and Q. So, A statement form is an expression made up of statement variables and logical connectives, which are the not, and or, that becomes a statement when actual statements are substituted for the component statement variables. The truth table for a given statement form displays the truth values that correspond to all possible combinations of truth values for its component statement variables. Let's see here. Let's do an example here. Evaluate the truth table for the following expression. P or Q, P or Q, or not P and Q. So you would make a truth table with P and Q as the first two columns. True, true. Then you would do one for P or Q. And that would be true, 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 false. So you take this, and then take this, put it down here. Doing that again with the A. And that would be true, false, false, false. Right? Break it down. Look at the parentheses, do the truth values for the inside the parentheses, and then move right along. And then you have the not P and Q, which is just the inverse of this one. So it'd be false, true, true, true. Did I? I did something wrong. This is not an or, it's supposed to be an and. Sorry. Another simple logical statement for everybody to learn. Just remember that when you're watching me teach. But anyway, so the final, this is this, and then the total would be this and that. So this parentheses and this negated here. So true and false be false. True and true would be true. True and true be true. False and true would be false. Step by step, you just break it down into easy, manageable components. You don't look at the whole thing together. You know, chopping down a forest, you do it one tree at a time, not the whole thing all at once. So break it down, do a column for each part, and then put it on in the total. Anybody recognize what this function is? I know some of you took a digital logic. Some of you might have taken it even with me last semester. So you should know what that function is. Or Intro to ECE. I covered it in Intro to ECE too. It's a digital logic circuit. Digital logic function, one of the 7 basic. Exclusive OR. That's an exclusive OR. It's true if one or the other is true, but not both. So one is true. If only one is true, then the final statement is true. If they both match, it is false. So, but anyway, I think that will be about it for today. Don't have time to get into the next section, but I will, like I said, I will postpone the homework until, I'll say Tuesday, so you have the weekend to do it. Quiz number 1 for chapter 1 up into graphs is on Thursday. Come with your notes printed if they're on a computer. If they're handwritten, that's fine. Just keep them organized and have them ready. So, quiz on Thursday. Have a good day.